All right, welcome to the Explainer. Today, we're diving into the hidden architecture of pretty much everything we do online, distributed systems. They're the invisible engine that powers your streaming, your banking, your messaging. And once you understand how they work, I promise you're going to start seeing them everywhere.
I mean, really think about it for a second. You tap a button on your phone and bam, a world of information is right there instantly. You hit plan a movie and it just starts. How in the world does that tiny request from your device get an immediate answer from a giant like Netflix or Google? Well, the answer is this incredibly powerful concept that's all around us, but it's almost completely hidden from view. So in this explainer, we're going to peel back the layers on this. First, we'll talk about why we have to go beyond just one computer. Then we'll look at the difference between the visible and the invisible ways these systems work. After that, we'll explore how all the pieces get connected. And finally, we'll look at the art of designing this invisible architecture itself. Okay, first things first, let's get the fundamentals down. What exactly is a distributed system, and why are they so absolutely critical in our world today? At its core, the definition is, well, it's actually surprisingly simple. A distributed system is really just a bunch of different computers or processors all linked together through a network. The best way to think about it is not as one single giant supercomputer, but more like a highly coordinated team of individual computers all working together to get the same job done.
Right, so why go through all this hassle? Well, the advantages are massive. First up, resource sharing. You can grab a file from a database from literally anywhere, not just the one machine where it happens to be stored. Second, computation speed up. You can take a massive, complicated job, split it up among a whole team of computers, and get it done way, way faster. Third, and this one is a real game changer, reliability. If one computer in the team goes down, the whole system doesn't crash. Another one just steps in and picks up the slack. And finally, communication, which is the glue that lets all these different parts talk to each other. These four pillars are the reason basically every service you rely on is built this way.
Okay, so we get why these systems exist, but how do we as users actually experience them? It turns out there are two really different ways this can all play out.
On one side of the coin, you have the visible approach. This is where you are fully aware you're dealing with a bunch of different machines. You have to manually log into a remote computer, run a command, and pull a file over. You are actively going to the data. But the other side, that's where the magic happens, the invisible approach. Here, the goal is to make all those separate computers feel like one single seamless system. You don't log into a Netflix server. The movie just comes to you. The whole experience is smooth. It just works.
And this quote right here, this gets to the absolute heart of modern system design. The pinnacle of success, the ultimate goal, is for you, the user, to have zero idea about the insane complexity humming away behind the scenes. It's all about engineering that messiness away to give you an experience that feels simple and, just effortless. So how do they pull off this magic trick? Well, it's all down to some really clever moves happening behind the curtain. The system can physically move data closer to where you are, so it loads faster. It can shift a really heavy calculation over to a computer that's not busy. That's called load balancing. It can even move the entire program you're using from one machine to another, mid-session, all without you ever noticing a thing. Which, of course, brings us to a crucial piece of this puzzle, the connections themselves. All this talk about teamwork and magic tricks is totally pointless if the computers can't actually talk to each other, right? So from a bird's eye view, we can basically split these connections into two main camps. First, you've got your LAN, or local area network. Think of the Wi-Fi in your house or the network in an office. It covers a small local area. Then you've got the WAN, or wide area network, which connects systems across huge distances. And the most famous WAN of all, of course, is the internet. And here's the key thing to understand, the big trade-off. LANs are ridiculously fast. We're talking up to 40 gigabits per second, precisely because they're local. LANs, on the other hand, have to connect cities and continents. So they're naturally going to be slower just because of the sheer distance the signal has to travel. You absolutely need both working together, that local speed and that global reach. Okay, so the computers are connected, we've got the networks, the wires, check. But that just opens up a whole new can of worms, right? In this massive, tangled web of connections, how does one little message from your computer find its way to the right destination?
Well, it really boils down to three main strategies. And the easiest way to get it is to think about a road trip. First, there's fixed routing. This is like using an old school paper map. The path is set in stone. It's simple, but totally useless if there's a surprise traffic jam. Next, you have virtual routing. This is like using a map app to plan your route before you leave the house. The path is fixed for this one trip, but you can pick a totally different one tomorrow. And finally, you have the smartest approach, dynamic routing. This is your live GPS, constantly checking traffic, looking for slowdowns, and rerouting you on the fly to find the absolute best path moment by moment. Modern systems are constantly mixing these strategies to get your data where it needs to go.
All right, so let's zoom back out. We've talked about the what, the why, and the how, which leads us to the grand finale, putting it all together. How do we actually design the invisible architecture that's going to power our future? You see, the goal today isn't just about raw speed anymore. It's about making systems robust so they don't break when things get crazy, and intelligent so they can adapt to problems all by themselves. It's a huge shift from just building for brute force power to building for resilience and intelligence. And this field is moving so fast to meet that challenge. We're seeing amazing new ideas like OpenFlow, which is a really cool concept for making the network itself smarter. It basically separates the brain, the part that makes routing decisions, from the brawn, the physical hardware that moves the data. This lets you manage traffic in a much more flexible and efficient way. It's like upgrading a whole city from simple timed traffic lights to a single, smart traffic control center that can adapt to everything in real time. You know, every single day, our world leans more and more heavily on these huge and visible systems. The challenge for the people building these things now isn't just about making them fast, it's about making them trustworthy. So the real question we're all facing is this: how do we design this invisible foundation so it's strong enough, reliable enough, and secure enough to actually hold up everything we're building on top of it?